Okay, guys. 11.1 is sequences, um, and this ought to be completely reviewed from what we did last year. We did pretty much everything that you're being asked to do in 11.1 and 11.2. So before we actually get started on 11.1, let me break down the chapter for you and let you know what's coming. There are sort of different schools of thought as to how one should break down sequences and series, because it's kind of comes in pieces. And it's basically how to the different theories deal with how to present it so that it all comes together and crystallizes for the student. I've actually taught it both major ways, and I actually come down and I actually like the way that the Stewart book presents it. But you do kind of need a heads up as to where this is all headed. So in 11.1 and 11.2, this is all review, okay, of sequences and series, what we did last year in pre-cal. So it should be very, very straightforward. And there are discrete tasks that you're asked to do, and all of them should look very, very familiar. I've asked you over and over again to preserve and keep the notes and all the tests and everything that I gave you. So those ought to be a good sort of touchstone to go back and actually review. 11.3 through, let's see, what section is it? It's 11.7. These basically deal with a myriad of tests for convergence, and I'll remind you what that means, and divergence, okay, of infinite series. So we have, infinite series, whether they converge to a specific number, whether they diverge, and like I said, I'll remind you of what all that's about. The rest of the chapter from 11.8 on, 11.8 to 11.11 deal with not numerical series, but what are called power series, or sometimes more specifically Taylor-Maclaurin series. So basically, instead of an infinite sum of numbers, it's an infinite sum of variables. So it basically looks like an infinite polynomial. 11.11 deals with application problems, and I never taught those. They're just one of those application sections in the book that I never really thought was worth doing. I'm hoping that your teacher doesn't do them either. But basically, we have here what are called power series, and sometimes more specifically Taylor and Maclaurin series, and you'll understand what that means when we actually get there. So we're going to review sequences and series. When we get to series, we're going to reintroduce infinite series, which are basically infinite sums of numbers. Now, some infinite sums of numbers sum up to a finite sum. And that shouldn't really surprise us. That should sort of harken back to the improper integrals that we did back in chapter 7. But some of them, of course, are infinite. If the infinite sum is infinite, then it diverges. If the infinite sum is finite, then it converges. And there are different tests to determine whether certain numerical series converge or diverge. From there, we're actually going to then use those infinite numerical series as a springboard to talk about power series. And these are important because, let's just say, for instance, you have sine x, okay? Sine x is actually not, the way your calculator calculates it is not actually as sine x. Your calculator actually winds up using an approximation. It winds up using what's basically called the Taylor-Maclaurin polynomial. It basically is a truncated Taylor series, and it uses that in order to show it. So basically, this right here is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot 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 dot, and actually works out to n is equal to 0 to infinity, negative 1 to n. Remember, with respect to the sigma, n is your variable. So when you start plugging in numbers for n, the x's are going to remain, and you wind up getting this right here. But this is, so basically what your calculator does is it basically takes, the people who program, they go, well, we want sign correct to, 10 decimal places or something. There's a way of determining how many of these terms you need in order for it to be correct to 10 decimal places, and then they just truncate it. They just cut it off at some point, okay? And we'll learn exactly how to do that just a little bit later. So this is basically the meat of this section. This is where we're headed. This is where we want to arrive at. Basically 11.1 through 11.7 are basically preparatory sections. Now that's a heck of a lot of preparatory sections, and therefore it's easy to get bogged down if you don't know where things are headed. That's why I wanted to tell you where this was headed. Now, on the AP exam, the BC, like the AB, has 6 free response questions. You can bank on the fact that one of them is going to be a sequences and series question. Okay? So this is very, very important that we actually understand this material, and just keep in mind as we're getting as we're running through these, and it's just a series of tests for convergence and divergence, that these will actually wind up paying dividends once we get to the power series, and that's actually where this chapter starts to get a little bit fun. Okay, now from there, let's go ahead and let's actually start doing a few examples of 11.1 and sort of refresh our memory on what sequences are really all about. Now, like I said, there are a few discrete tasks that they'll be asking you to do that should be actually relatively familiar. Okay, the first task is given an a sub n, of course, which is our formula, right? Given our a sub n, okay, list the first 5 terms, okay, which ought to be really, really easy. So let's say I'm given a sub n is equal to 2 minus 4n, okay? So you just start plugging in 1, 2, 3, 4, 5. So you plug in 1, and that's 2 minus 4, or negative 2. You plug in 2, and you wind up getting 2 minus 8, which is negative 6. And then, of course, you start recognizing the pattern, and you can go ahead and do this, right? And remember, sequences, the way I defined them last year, is they're just a list of numbers with a discernible pattern. This is the explicit way of actually sharing what that pattern is. Okay, so basically we've been given an a sub n, and we just go ahead and list it out. Okay, well, let's do another couple of examples. If we have a sub n is equal to sine n pi over 2. Well, like I said before, just go ahead and start plugging in numbers, right? Plug in, and we always start with 1 unless we're specifically told otherwise. Go ahead and plug in 1, and I get sine of pi over 2. And then, of course, plug in 2, and I get sine of pi. And plug in 3, and I get sine of 3 pi over 2. And then plug in 4 and get sine of 2 pi. And then sine of 5 pi over 2. Well, of course, those have actual values, right? Sine of pi over 2 is 1, 0, negative 1, 0, 1, and dot, 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 all the way out, right? Now, of course, there are other ways to actually get this string of numbers. This just happens to be one of them, okay? So let's go ahead and do one more before we go on to something a little more difficult. Let's say we have a sub n is equal to 5 minus 1 over n plus 1 over n squared. Okay, and I want to actually plug in and actually get values. Now, you can leave it in this form. You can actually, 5n squared minus n plus 1 over n squared if you want. Depends on which you think is easier. If you plug in 1, you get 5 minus 1 plus 1. Okay. Plug in 2, and you get 5 minus 1/2 plus 1/4. And you get 5 minus 1/3 plus 1/9. You get 5 minus 1/4 plus 1/16. And then 5 minus 1/5 plus 1/25. And from here, obviously, these are all a little bit less than 5. Okay, if we simplify, we're going to get on the first one, that's going to be 4. Okay, Now, these two together wind up being minus 1/4, so that's 4 and 3/4. This one winds up being minus 2/9, right? So that winds up being 4 and 7/9. This one winds up being minus 3/16, so that's 4 and 13/16. And then of course from here that winds up being 4, and that winds up being negative 4, minus 4/25 once you get a common denominator. So that's 21/25. Okay? And then of course, and there would be another way to actually, write that probably. I mean, that's a very discernible pattern right there, okay? So sequences, if you're given an a sub n, especially if it's in explicit form like this, where a sub n basically allows you to find, if you want to find the 17th term, it's very easy. You just plug in 17 and it actually gives you the 17th term. Okay, well that's Mickey Mouse stuff. Okay, well why go over it? Well, you have to remember, and I told you this last year, and I'm hoping you remember, that these are functions. Now we've gone and we've played with functions so much that we assume that functions have to form curves and have to be, have to actually have an interval for a domain and stuff like that. Well, that's not the case. If you remember the way that we define functions all the way back in Algebra 2, it's simply the fact that given inputs, every input has exactly one output. Well, these are functions. A sub n just happens to stand in for f of x, and a sub n will only allow you to plug in natural numbers. So basically, these are functions where the domain, of course, is the natural numbers, of course, which is what we 1, 2, 3, 4, and on all the way out, okay? And for each input, you're going to get a very specific output, okay? Or for every output, you're going to have a specific input. So you remember the definition of a function. That's really what matters. So let's actually now do the second task that we might be asked to do. We need to go the other way. So given the first 5 terms of a sequence, discern the pattern and give it to me in an a sub n. Now this is a little bit more difficult, okay? But let's go ahead and do it. Let's say we have 2/3, 3/4, 4/5, 5/6. Now especially, I told you this, especially if it's rational, we need to go ahead and break it apart and just see if we can find a pattern to the numerator. If we can find a pattern to the numerator, that's going to help us, okay? And so what we have here is we realize that in the first term, the numerator's 2. In the second term, the numerator's 3. In the third term, the numerator's 4. So the numerator is always 1 ahead of whatever term we're talking about. So if this is the nth term, then the numerator is n plus 1. Well, we also happen to recognize that the denominator is doing much the same thing, okay? And it is progressing as 2 ahead of that. Well, this can actually, I mean, if you notice this is 1 minus a third, 1 minus a fourth, 1 minus a fifth, 1 minus a sixth. So the fact that it was given to us like this in no way contradicts the fact that we could have actually done that. Now this is a perfectly legitimate way to do it. Now granted, if it's in this form, it's most likely going to look like this, okay? But those are equivalent, okay? All right, well, let's go ahead and do one that's a little bit more difficult. How about if I give you, and I think I did this one with those that were on the Skype session, but I think it's a pretty important one. Now remember, when we're dealing with sequences, there are 2 special types of sequences that we dealt with. Okay? Now those don't exhaust all of the number of sequences. There's an infinite variety of sequences out there, but there were 2 special ones that we dealt with. Okay? There were arithmetic okay, and geometric. Arithmetic basically were like linear functions, okay? And they had the form of, they basically look like a linear. Geometric look like exponential. Now, this progression looks like neither, okay? But you got to remember that when we were going through this, we actually did a couple of examples like this, and I remember mentioning this to you, but it was sort of a passing comment, and I'm not sure how many people actually remember it. We identified an arithmetic sequence when there was a common difference, okay? Well, here the difference is not common, okay? At least not here, okay? The difference between -1 and 2 is 3. Between 2 and 7 is 5. Between 7 and 14 is 7. Between 14 and 23 is 9. Now, those are consecutive odd integers. What else progresses by consecutive odd integers? I'm going to give you a second to think about that while I show you the fact that if you go 2 layers deep, you actually do have a common difference. So if you go 2 layers deep and you find a common difference, that is a good indication that you have a quadratic a sub n. And this just happens to be 2 less than 1 squared. This is 2 less than 2 squared. This is 2 less than 3 squared. This is 2 less than 4 squared. This is 2 less than 5 squared. So my a sub n is simply n squared minus 2. Now, of course, if you were to go 3 layers deep and find a common difference, that would be a good indication that it was cubic. Okay. All right, let's go ahead and let's talk about the difference between explicit and recursive, okay? And because that's something that we don't run into it all that often, but it is actually incredibly important to know. Now, let's say that we have, 3, 7, 11, 15, 19, 23. Now that's a very easy arithmetic one, right? We recognize that the common difference is 4. And, if I ever asked you to do that, you would say, well, that's, a sub 1 plus d times n minus 1, which is the formula for an arithmetic sequence. And the first term is 3. The common difference is 4, right? And of course, you can simplify that a little bit and wind up getting -1 plus 4n, right? This is what's called explicit. Explicit basically tells you if you want the nth term, you go ahead and plug in and you can find the nth term, okay? Recursive sequences are not defined in the same way. Recursive, the logic of it is not how do I get the nth term. The logic is how do I get to the next term. So basically this, usually they give it to you like this, and usually they use k, okay? So they're going to give you the first term, and then they're simply going to tell you how to get to the next term. If I know the kth term, I simply need to add 4 to get to the next term. So whatever k is, k plus 1 is 1 higher, and therefore the next term. This tells you how to get from the second term to the third term to the fourth term, the fourth term to the fifth term, and this is what is referred to as a sequence defined recursively. This is a recursive sequence, okay? Now there are a few more things that we need to cover in 11.1, and I'm going rather fast because, quite frankly, this should be review. But we'll probably do one more video on 11.1 before we move on to 11.2. In fact, most of the sections in this chapter, because even in 11.3 through 11.7, there's only one concept that needs to be mastered per section. We'll probably go with about 2 videos per section, especially since there are so many sections in this chapter. And we'll shore that up with supplemental videos if they're requested and if you need them. But go ahead and be looking for the second video on 11.1, and then we'll move on to 11.2 and then on to tests for convergence and divergence. Bye.